Hello, hello. Better? Okay. So the fundamental theorem of arithmetic says that any number can either be a prime or it can be expressed as a product of primes. So how will you test given any number? How will you test whether that number is prime or not? That is known as primality testing. Okay. So for example, n equal to 401. Now the first approach is you try to divide it by prime numbers starting from 2 up to square root of n. Okay, so in this case we started with 2, 3, 5, so up to 19 was sufficient. Okay, if none of these primes divide the given number, then the given number is a prime. Okay, now why is it sufficient to go only up to square root of n? Okay, so for example, let's say 401, assume, okay, assume that 401 is a product of two primes A and B, let's say. Okay, so either A will be greater than B, or A will be equal to B, or A will be less than B. These are the only three possibilities that are there, right? So consider this possibility. Okay, if A is equal to B, then your n will be a perfect square. N will be a square. Okay, so in this case, A will be equal to B will be equal to square root of n. Okay, n will be a perfect square and A and B both will be square root of n. In all other cases, in all other cases, you see, if A is greater than B, okay, then still B will be less than square root of n, and if A is less than B, then A will be less than square root of n. Okay, to compensate, right? A into B, any number if you have to express as A into B, if A is small, so let's say we were talking about 402. So if A is small, or take any number, you get the point. If A is small, then B has to be greater to compensate and to give the same product. And if B is small, then A will be large, but the smaller one of the two. So if B is the smaller one, then it will be less than square root of n. If A is the smaller one, it will be less than square root of n. So while testing, so one of the factors of any number, one of the factors of any number, however large, small, however, whatever number it is, one of the factors of it will be within 2 to square root of n. Okay, so this approach is also called as trial division, because we are taking trials, we are trying to divide by all the primes to square root of n. Okay, now there is another technique which is not very efficient, but slightly, you can call it as a trick, let's say. Okay, just tell me the RHS of this identity that I'm going to tell you. What is the RHS? it is a product of two terms. Yeah, it is x plus y into x minus y. Okay, so any number, if you can express it as a difference of two squares, then it is composite. Okay, if n is equal to a difference of two squares, x square minus y square, then n is composite, and these are the factors. N is composite, okay, not prime. Okay, so for example, okay, for example, if I say 493, 493, so 493 is 23 square is 529 minus 4 square. No, sorry, 6 square. Okay, I meant 6 square. Okay, therefore, it is the product of 23 minus 6, it is 17, and 23 plus 6, that is 29. Okay, so this is a composite number. So given any number, this is your n that is given. How will you find out whether it is composite basically? So the first way is, okay, so n is equal to, we want to find whether n is equal to x square minus y square. Now this can also be written as n plus y square, taking y square to this side, n plus y square equal to x square. That is, you add a square, to n. Okay, and if the result is a square, then n is composite. Okay, did you get this point? Yes. So what you will do, you will start, okay, so you'll take n and you will start with the smallest square. You do n plus 1, check whether n plus 1 is a square. Okay, 493 plus 1 is not a square. Second, n plus 4, you add all the square terms. N plus 4 is 497, still not a square. N plus 9. Now for this method or this trick, you can say you should be like you should know the tables up to squares up to 30 at least. Okay, so that will be useful. So you know, n plus 9, 502 is not a square. N plus 16, not a square. Okay, n plus 25, and finally for n plus 36, you will find that n plus 36 is 529. Okay, so n plus 36 is 529. 529 is 23 square, 36 is 6 square, and therefore we found the uh, n as the difference of two squares. Okay, so this is one way. Okay, you can, okay, I'll give you another example, simple one. 247. 247. Tell me the factors. Tell me the like, okay, test for it. First of all, I'll say test for it whether you can find the factors. Let me know. Very simple one actually. Yeah, it is 256 minus 9. Okay, so 16 and 3 are not the factors. 16 square minus 3 square, which is 16 minus 3 into 16 plus 3. So the factors are 13 and 19. All right, 13 and 19. Okay. Yeah. Okay. So factors means what? You multiply the factors to get the number. Okay. So if we find the factors, then the number is obviously composite. Number is not prime. So what we are doing is we are adding square terms. Up to this part, it was clear, right? So we are adding square terms to n. So 247 plus 1 is 248, not a square. 247 plus 4 is 251, not a square. 247 plus 9 is 256, which is a square. Okay. So 247 is 256 minus 9, which is 16 square minus 3 square. So 16 square minus 3 square means by the identity x square minus y square is x minus y into x plus y. I wrote this step. Therefore, it is 13 into 19. Therefore, 13 and 19 are the factors of 247. Okay? Fine. This is one way. Uh, Another way can be, again taking this same identity, that is n is equal to x square minus y square. This is the same equation. You can manipulate this as y square equal to x square minus n. Y square is equal to x square minus n. Now what you do is you find a square, number that is square, that is, I should say, the closest square. Find the closest square. Just find the closest square larger than n. Find the closest square larger than n. Start with that, and then you can do that. Subtract n from it. Subtract n from it. And check whether the result is a square. Okay. So again, you should know the squares for this technique. Okay, so if I say 20 square is 400, 21 square is what? 441, 22 square is 484, 23 square is 529. Okay, so 493, the nearest larger number square to it is 529. Subtract it and you will get 36. That is one way. Similarly for 247, if you see, 15 square is 225, 16 square is 256, So 256 minus 247 is 9. Okay. Now you may not get it. Uh, like, so you may have to try for one more square. Let's say. So this. So luckily, like we got it in this way, but maybe we could require to go up to the next. So let's say, for example, it was uh, 64 or something. Yeah. So it may not be that the closest square will give you the answer. You may have to try for one more or two more such terms. But this is another way to calculate the or to get the factorization basically. Basically, you want to find x square and y square. Do it by any way possible. Okay, so it is one way. But here in this case, there is no bound as such. There is no bound. So in this method, what you can do is uh, because you have to find where to stop looking. If it is actually a prime, you will have to stop looking at some place. Okay. So what we can do is where we can stop. Okay, let's say in this case. Okay, so for example, in this case, 16 square minus 247 is 3 square. So you can start with ceiling of square root of n. Okay, what do you think? Where can we stop? If it is a prime, where should we stop? Till square root of n. Yeah, yes, because you know if let's say if n was a perfect square, again you take that case. If n was a perfect square, then you would get that it is 256 minus 0, right? So the same idea. Okay, to square root of n, time before the square root of n. That is for trial division. Prime before the square root of n. That is for the trial division. In this case, just keep in mind that if it is a perfect square, then you will go up to you would go from 2 to 16 in this case. Not 2 to 16, but get the point. Up to square root of n. So okay. So this method is also called as Fermat factorization. Okay, Fermat factorization is it's also called as. Uh, okay. There is one more test for primality apart from these techniques, which is called as Fermat's primality test. Okay, so this test is for, so now one very obvious thing is a prime number has to be an odd number basically. Okay, so n must be odd first of all. Okay, prime number has to be an odd number. Then you choose b between 1 to 1 to n. Choose b between 1 to n. Now you can take b as anything. So we'll see an example. So if b raised to n minus 1 does not have an inverse modulo n, then n is composite. Then n is not prime. Then n is composite. If you recall the Fermat's theorem, what Fermat's theorem said was that if p is a prime number, then okay, I'll use the same alphabet, or let's use the Fermat's theorem's terminology. So a raised to p minus 1 is congruent to 1 modulo p minus 1. This was the Fermat's little theorem. Okay. Right, and p does not divide a, right. This was the Fermat's little theorem. Now analogously, sorry, this is p, not mod p minus, this is p. This is mod p. Okay, so if this theorem does not hold, so we used n here, b and n. Okay, so just see the analogy between the two theorems. This is the Fermat's primality test, which is based on Fermat's little theorem actually. Okay, so for example, we want to check whether 209 is prime. Okay, now let's take b as 2. Now what do we want to find? B is 2 to the power 208 is congruent to what modulo 209. or let's say what, x congruent to x modulo 209. Okay, so x is congruent to modulo 209. Now what will you, how will you calculate? Two raised to 208. So you'll start with 2 square, let's say 2 square is congruent to 4 modulo 209. 2 raised to 4 is congruent to 16. 2 raised to 8 is congruent to what? Not 32. Modulo 209 we are calculating. 47 is correct. So 2 raised to 8 is congruent to 47 modulo 209. Yes, 256 mod 209 is 47. Remainder. Okay. Then 2 raised to 16. This you'll have to calculate actually. So 47 square modulo 209. You'll have to calculate that. 47 square mod 209. 119. Yes, is correct. Then and 119 square modulo 209. This is repeated squaring approach that we are using. 158. Correct. 2 raised to 64. 93. Are you doing it on your calculators or what? Your calculators are supporting such large exponents? Okay. Another way is we can use some tricks or something like this is straight away repeated squaring that we are using. 2 raised to 128. I don't know whether, so instead of a, come on, 2 raised to 128, 93 square mod 209. 93 square. Okay, 80 is correct. Okay, now 2 raised to 208 can be written as 2 raised to 128 into 2 raised to 64 into 2 raised to 16. Okay, and from the values that we have calculated, 80, this is mod 209, This is 80. This is 93. And this is 119 mod 209. Okay, just calculate this. 36. 36 is correct. 36 mod 209. But essentially, so it is not congruent to 1 modulo 209. Okay, thus 209 is composite. Okay, so this is time consuming, but this is how it works, and it is normally automated. So also note that this is not a see I, this so true primality tests are much more time consuming and much more complex than this. This is just we are proving the negative. That is, we are proving that whether the number is composite. So, okay. So an interesting fact about it is okay. We have to take B as arbitrarily. Yes, we can, but take the advantage of the fact that so B can be anything between 1 and n. So we can choose B as 2 always. We can choose B as 2 because we know the powers of 2. Yes. Jitesh, are you saying something?
No, sir, by mistake. So,
So what I was saying was, huh. So if if Fermat's primality test, if this test says that n is composite, if this test says that n is composite, then n is definitely composite. Okay. However, however, it may be the case. It may be the case that b raised to n minus 1 is congruent to 1 mod n for uh, some case, even when uh, n is composite. So when it says that a particular number is not composite, then it may not be true. Okay. So these form a special category of numbers. Okay. So the numbers for which a composite integer n, for which b raised to n minus 1 is congruent to 1 mod n is called is called b pseudo prime. Now b pseudo prime means if the b with which we tested was 2, then it is called as 2 pseudo prime. So one example of such a number is 2 raised to 340. That is 340. Okay. Example is n equal to 340 is one such case. So 2 raised to 340, if you test it, it is congruent to, sorry, not 340, 341. So 2 raised to 340 is congruent to 1 mod 341, whereas 341 is actually composite, is 11 into 31. Okay, so 341 is a 2 pseudo prime. Two pseudo prime. Similarly, there are some other examples for base 3. One of the numbers is 90. Sorry, again, not 90, 91. Okay, so 3 raised to 90 is congruent to 1 mod 91. Even though 91 is actually 7 into 13. Therefore, 91 is a 3 pseudo prime. Okay. Okay. So this was about primality testing, factorization. Now the next thing to cover is, okay, any questions, any doubt up to this point? Can you explain the pseudo prime part again? Okay. So if you believe this primality test, okay, okay, if I say that the Fermat's primality test is perfect, then what the Fermat's primality test says that if b raised to n minus 1 is not congruent to 1 mod n, then n is composite. Okay. Now, what is the converse of this statement? The converse is that if b raised to n minus 1 is congruent to 1 mod n, then n is prime or not composite. Okay, I'll repeat this statement again. The converse is if b raised to n minus 1 is congruent to 1 mod n, then n is not composite. Converse. So, what happens is actually there are some numbers for which b raised to n minus 1 is congruent to 1 mod n, and if we believe in the theorem, we'll say that b raised to n minus 1 is congruent to 1 mod n means that n is not composite. N is not composite. B raised to n minus 1 is congruent to 1 mod n, then n should not be composite as per the Fermat's primality test. However, there are some numbers for which b raised to n minus 1 is congruent to 1 mod n and still the n is composite. So such numbers are called as pseudo primes. Okay, numbers for which this holds and still they are composite. Okay, okay. So the point behind all this was, you know, there are certain. Uh, so what did we learn from all this? What did we learn from all this? Like from uh, the previous lecture, actually, first we saw the discrete logarithm problem. From that, we saw that it is difficult to take the logarithm and find the exponent. So it is difficult to crack the Diffie-Hellman key exchange as well as the RSA. It is difficult to crack it because even if you know the public key, taking the logarithm is not easy. To know the private key, if you take the discrete logarithm, it is very time consuming and it is not easy. And to make it even more time consuming and complex, you take very large prime numbers to the tune of 100 digits long prime numbers. Okay. Then in today's lecture, what we saw that factorization. So in the RSA algorithm, n is equal to p into q. N is equal to p into q. Okay, and then you find the totient of n, and then the further calculations are done in case of RSA. Now, even if the n is public, even if n is public, it is difficult to factorize n to find p and q. Okay, it is hard to factorize. Okay, it is hard to factorize n to find the p and q. P and q both are primes. Okay, so if you have solved any RSA question uh, ever, so the first step is you have to choose two primes p and q. Then you calculate n. Then you calculate totient of n, and then you uh, move further, choosing the uh, public key and then choosing the private key, so on. So cracking n is not possible because it is hard to factorize. Then finding prime numbers. Okay, so finding whether a number is prime or not. And in fact, the actually if we study primality testing in detail, so it will take a very long time if we study the entire primality testing in detail. But we arrive at some point where we have to generate a number. Okay, we have to generate a number, large one, and we have to decide whether it is prime or not. The other way is we generate a prime. Okay, we generate a prime number. Okay, so when we are when we say that 100 digits long prime number, how do we know? How do we generate that 100 digits long prime number? How do we generate a prime number? In fact, okay. So I'll just give an example of it. Uh, which theorem I introduce? No, there is no easy. I'll just tell you the. So basically, there are certain numbers called as Fermat's numbers. Fn is equal to 2 raised to n plus 1. 2 raised to 2 raised to n plus 1. Now, what is the speciality of these numbers is that there is a test for these numbers, an easy test by which you can check whether a Fermat number is prime or not. Okay. So, a Fermat's number is prime if 3 raised to fn minus 1, that is 2 raised to 2 raised to n, divided by 2, that is 2 raised to 2 raised to n minus 1, is congruent to minus 1 mod fn. Okay, this is called Pepin's test. Okay. Similarly, there are something called as Mersenne numbers. Mersenne number is defined for MP, where P is a prime. So it is 2 raised to a prime number minus 1. 2 raised to prime number minus 1. Okay. For these numbers. Okay, so as a fact, Mersenne numbers have been used to generate the largest prime numbers. Okay, so we define a sequence for the test as S0 is 4 and Si plus 1. This is a sequence that we are defining. Si plus 1 is equal to Si square minus 2. Okay, so 4. Then Si plus 1 is 4 square minus 2. That is 14. Then so this is, I should have written this is S0, this is S1, S2 is uh, S2 is 14 square minus 2, it is 194. Okay. This is the sequence. Now MP is prime when, if and only if S of P minus 2 is congruent to 0 mod MP. S of P minus 2 is congruent to 0 mod MP. Okay, so for example, okay, so if P is 7, let's say P is 7, we are generating primes now. Okay, so P is 7. So M of 7 is 2 raised to 7 minus 1, which is 127, and we want to find whether 127 is prime or not. Then what we do is, now we'll not calculate directly, we'll find mods. So 4, 14, 194 mod 7. Find 194 mod 7. Sorry, 127. 194 mod 127. 194 mod 127. Okay, can you repeat? Okay, which part to repeat? Mersenne primes, I'll repeat again. So, Pepin. Okay, Pepins, this is what it is. Okay, 3 raised to fn minus 1 by 2 is congruent to minus 1 mod fn. We are not interested in this. Mersenne numbers are simpler, you can do it. Okay, so, in tutorials or in exams, like this is possible to be calculated in the exam time. So, let's focus on this. So, yeah, 67 is correct. Then 67 square mod 67 square minus 2 mod 27. This formula 67 square. Next term will be 67 square. Mersenne number is first of all it is defined for only prime numbers. Okay, so let's say we take any prime number p equal to 7. So Mersenne number is 2 raised to that prime number minus 1. Okay, so m7 is 2 raised to 7 minus 1. This is the Mersenne number m7. Now we want to check whether the Mersenne number is okay. So this is the generating part. We generate the Mersenne number, and this is the test. This is the test to find whether it is prime. Okay, is it clear up to this part? How is this definition clear? Mersenne number MP is 2 raised to p minus 1. So m raised to 7 is 127. Okay, Aditya also? Yes? Okay. So now we have to check whether 127 is prime or not using this technique. Okay. So what we do is now we can also use that square and all the techniques that we saw before. But this test or this technique, what it does is you have to generate a sequence. That sequence starts with s0 equal to 4. It is defined that way. Okay, it starts with s0 equal to 4, and for every consecutive, every next term, what you have to do is the next term, that is si plus 1, is the previous term square minus 2. Okay, so this is the sequence. This is the sequence. Now MP is prime if and only if SP minus 2 is congruent to 0 mod P, mod MP. Okay, fine. So because we are going to take mod MP, I took it directly over here. So like 4, like S0 mod MP. Now here MP is 127. So 4 mod 127 is 4. 14 mod 127 is 14. 194 is S2 actually. S2 is 194. 194 mod 127 is 67. Okay, calculate the next term. 60 next term will be 67 square minus 2 mod 127. Yeah, 42. 42 is correct. Let's proceed. 42 square minus 2 mod 127. 42 square minus 2 mod 127. 111 is correct. Now 111 square minus 2 mod 127. Yeah, yeah, yes. This is 0. This is 0. You got a 0. Now will you keep doing this forever? No. The test says that SP minus 2 must be congruent to 0. Okay. So p minus 2 means p is 7 here. So we'll go only up to 5. So this is S0, okay, this is S1, this is S2, this is S3, this is S4, and this is S5. S5 is 0 as wanted. S5 is congruent to 0 mod 127. Therefore, 127 is a prime. Okay?
Excuse me, sir.
Yes.
Sir, for every sum, the sequence will be defined as S0 will be always equal to 4.
Yeah, S0 is always 4. You'll always start with 4.
Okay, sir.
Okay? Any other questions anyone has? So, what are we doing in this case? We want to generate large prime numbers. Okay, so we generate the number using this formula, mp is equal to 2 raised to p minus 1, where p is a known prime. P is a known prime. Okay, so 2 raised to p minus 1 will generate a number, and then using this test, we can check whether the number is the result, that is mp is prime or not. This is used for generating large prime numbers used in the algorithms like RSA, whatever the cryptographic algorithms that you want, whether it is Diffie-Hellman key exchange, whether it is RSA. Okay, the prime numbers they require are generated using this method. Okay, no questions. Okay, then I'll end the lecture here. Thank you.